Hello everyone, welcome back to Physics 425. In this video, which will probably be a little bit of a shorter video, I want to see if we can answer intuitively a couple of questions about liquid helium. And so the first question is, what makes liquid helium special compared to other cryogenic liquids like liquid hydrogen and things like that? And then the second question is, we have two isotopes of helium, and why does helium-3 have a lower boiling temperature than helium-4? Okay, so first, why don't we start with just a couple of useful bits of information about liquid helium. And so let's first write down the boiling temperatures of the two isotopes. And so we have helium-3, and at 1 atmosphere, its boiling temperature is about 3.2 Kelvin. And helium-4 has a boiling temperature of about 4.2 Kelvin. The density of the liquids for helium-3 is 0.082 grams per cubic centimeter, and for helium-4 it's 0.145 grams per cubic centimeter. Okay, so we can see that the difference in density is almost a factor of 2, not quite a factor of 2, but the difference in mass of the two isotopes is, 3 nucleons to 4 nucleons, and so it's not a factor of 2 difference. So there's something else going on besides just the mass of the helium atoms that's contributing to the difference in densities. And then there's also the latent heat, so the heat required to convert a certain volume of liquid into vapor. And so the molar latent heat for helium-3 is about 30 joules per mole, and it's about 85 joules per mole. And so there, that difference is almost a factor of 3. Okay, so the first thing we'll do actually is think about that first question: why is helium special when compared to other cryogenic liquids? And so the first thing to note is that in helium, whether you're talking about helium-3 or helium-4, the binding forces between helium atoms are very weak. They're very weak because helium has a completely full valence shell. And so if we were to draw a helium atom, I'll draw the 2 protons in the nucleus. If it was helium-3, there'd be 1 neutron in the nucleus. If it was helium-4, there'd be 2 neutrons. And then it has only 1 electron shell, and it's got 2 electrons in there, so that's the 1s shell, and it's completely full. And so the electron configuration of helium is 1s2. So specifically, the valence shell is completely filled. Okay, so if you think back to, I don't know, something like silicon, then in silicon, binding between atoms in a solid is this covalent bonding where you share electrons in the valence shells between neighboring atoms. And so you can't have anything like that in helium, and the bonding between, or the attraction, not the bonding, the attraction between atoms is determined by a van der Waals force between non-polarized atoms. And this is very weak. So there's very weak attraction between helium atoms in the liquid. And let's just make a note that whether you're talking about the helium-3 isotope or the helium-4 isotope, they behave identically chemically, because they have the same electron configuration. If you were thinking about something like hydrogen, so we'll say in contrast, something like hydrogen has a larger polarizability, and that leads to a stronger attraction between atoms. And so if the atoms are much more strongly attracted to one another, then you can imagine when you're trying to boil the liquid, or you're trying to have some of the atoms escape the surface of the liquid and become vapor, it's harder to do when those atoms near the surface are attracted to all the other hydrogen in the liquid. And so the result is that the stronger attraction between atoms leads to a much higher boiling temperature, which for hydrogen is about 20 Kelvin. So because of the weak interactions between helium atoms, the liquid does not solidify at any temperature except when under high pressure. So just to give a sense of what that is, liquid helium-4 will solidify at 1 Kelvin when the pressure is 25 atmospheres, and liquid helium-3 solidifies at 1 Kelvin when the pressure is about 34 atmospheres. Okay, what some of these numbers start to tell us is that, well, it looks like the attraction between helium-3 atoms is weaker than it is between helium-4 atoms. For example, helium-3 requires higher pressure to solidify. Sorry, where is that here? And so that presumably is due to a weaker interaction between atoms. If we go back to this list over here, the latent heat, the heat required to vaporize the liquid, is higher in helium-4 So that must mean that helium-4 atoms are slightly more attracted to one another than they are in helium-3. And so that's something that we're going to try to understand. Okay, so just to summarize some of this, the weak interactions explains the difference between helium and other liquids. And so that's kind of a bit of a understanding of that first question. And so the second question is essentially is about what are the differences between helium-3 and helium-4, and what are those differences due to? So the clue, or the hint, is going to be that helium-3 has a lower mass than helium-4. And so let's see what that is going to lead to. What we're going to try to do is we're going to try to discuss this concept of zero-point energy. And so it's going to be the minimum amount of energy that must be associated with interacting atoms. So to do this, we're going to model an interacting atom, or interacting atoms as our harmonic oscillator. Okay, and so just to have the simplest possible picture, let's just imagine, for simplicity, a 1D oscillator. So there's some helium atoms connected by springs. The energy of a harmonic oscillator, so if we take one of those atoms, it's going to have some kinetic energy determined by p²/2m, and it's going to have some potential energy determined by the spring stiffness K, and how much that spring has been either stretched or compressed, x². Just to remind you, if you had a harmonic oscillator, it would have a natural resonance frequency, omega, and that's determined by the square root of k/m. Or, solving for k, that would be omega² times m. Oh wait, so if we invoke the uncertainty principle, what the uncertainty principle tells us is that the product of delta x and delta p, the range of the uncertainty in the position and momentum of a microscopic particle, has to be greater than or equal to h⁻². So if we take the minimum possible of the uncertainty principle, then the uncertainty in the momentum is going to be h⁻² delta x. So that means that the energy of our harmonic oscillator must be at least, okay, what would it have to be at least? So p²/2m. So for p², we'll say that that has to be at least this h⁻² delta x². So we get h⁻²/4 delta x², but then there's also a 2m, so this becomes 8m delta x squared plus 1/2 kx squared, but k is going to be omega squared over m. So that's omega squared times m. Omega squared times m, and then we have a delta x squared. Okay, so what we could try to do is we could try to minimize this. So let's minimize with respect to delta x, and so we could try to evaluate the derivative of this energy with respect to delta x, set that equal to 0. And so let's see, what do we get? So we would have minus 2 h bar squared over 8m delta x cubed. So the minus 2 comes from the delta x to the minus 2. And then we would have plus omega squared m delta x. And we're going to set that equal to 0. And so let's see, what do we get? We get omega squared m delta x is equal to h bar squared over 4m delta x cubed. Solving for delta x, we would get delta x to the 4th is h bar squared over 4m squared omega squared, or delta x squared is equal to h bar over 2m omega. Or in fact, actually, what we could do is let's solve for omega and sub into our expression for E. So omega is equal to h bar over 2m delta x squared, and we're going to sub that into here. So our first term doesn't change. E is equal to, the first term is h bar squared over 8m delta x squared. And then the second term is 1/2 m delta x squared omega squared. So it's plus 1/2 m delta x squared, and then times omega squared would be h bar squared over 4m squared delta x to the 4th. Delta x squared cancels with 1 over delta x to the 4th. And what you can see actually is this minimization has made the two terms equal to each other. So we end up with h bar squared over 8m delta x squared, and we have two of those terms. And so this E naught, let's say after we've done the minimization, the minimum energy E naught, which is the 0 point energy, is h bar squared over 4m delta x squared. And so this is the 0 point energy. And the important point, if we go back now and start to think about the differences between helium-3 and helium-4, is the mass. So the 0 point energy is inversely proportional to the mass, and so if helium-3 has a lower mass, it has a higher 0 point energy. So E0 is proportional to 1 over m, and therefore what we say is helium-3 has a larger 0-point energy, than helium-4. If it has a larger 0-point energy, then you can imagine that it's vibrating more vigorously than helium-4 atoms would be in liquid helium-4. And so therefore, helium-3 atoms have more kinetic energy, or more energy in general if it's part of this harmonic oscillator, and so it's oscillating more vigorously. And that means that helium-3 is easier to evaporate. So it has a low boiling temperature and a low latent heat of vaporization. And it's also harder to solidify, right? Needs more pressure. When compared to helium-4. Okay, and so this difference between helium-3 and helium-4 is really a quantum effect, because we had to invoke the uncertainty principle in order to evaluate this 0-point energy. One last point is we can make an estimate of this delta X. Delta X, if we took 1 mole of helium-3 atoms and put them in the liquid state, we could determine the molar volume of the liquid. And then if we divide that molar volume by Avogadro's number, we would get the volume occupied by a single atom. And if we take the cube root of that volume, that approximately tells us delta X, the 1D space occupied by a single atom. So if Vm is the molar volume and we divide by Avogadro's number, then that ratio tells us the volume occupied per particle. And if we take the cube root of that, then we get a one dimension, the space occupied by a single atom in one dimension. And so Vm is the molar volume of the liquid. Of course, this works for either liquid helium-3 or liquid helium-4. Okay, good. So, like I said, I think this was going to be a short video, but it kind of develops some intuitive idea for what makes helium special among the other cryogenic fluids, and it's the very weak interactions between the atoms with filled valence electron shells, and then also distinguishes the differences between helium-3 and helium-4. In fact, a little later, we'll look at the differences between helium-3 and 4 again, and we'll see that there's actually some more significant fundamental differences, and that is that the helium-3 particles are fermions, and the helium-4 particles are bosons, and so that means the way they behave at very low temperatures is drastically different due to the difference between the fundamental statistics of collections of fermions at low temperatures and collections of bosons at low temperatures. And so that's something that we